Yo, Chuck.
This video is going to be on depth first search, and all depth first search is just a way to traverse a graph. So here you have a graph, which is just a series of interconnected nodes, A, B, C, D, E, and F. We're going to start on A. You would call this the root node, but this is the very first node we're going to start. So the way depth first search works is we're going to first put A, or the root node, in our call stack. Now, the way a call stack works is whatever is on top is popped off or called, and that is executed. But the key being that whatever is on top is executed first, okay? So right now we only have one node to execute on, so there's no need to be confused as to what's up next. It's going to be A. So we're going to visit A. So now you can see in our visited nodes, we've now visited A. And because we visited A, we get access to both of A's neighbor nodes, which are B and D. First, B is put on the call stack. This is because it's on the bottom, and then D is put on the call stack after that. So D is on the top. But remember what I just said, that when you have a stack, the thing on the top is executed or popped off first. So B isn't going to be called first. D is going to be called first. So we're going to call D, and notice now we visited D, and B is still at the bottom getting no love, and now E, the neighbor of D, has now appears on top of the stack. So actually, E is going to get called before B is. So let's do that now. We call E, and now we visited E, and because we visited E, just like before, we're going to gain access to E's neighbor node, which in this case is F. So again, F is going to be on top of the stack, and it's going to be executed and given priority before B. So poor B is just alone right here. So we're going to execute F. Now we've visited F, and B has not been visited yet. So you might ask yourself, wait, we've just traversed A, D, E, and F. How do we get backwards to B? Well, B is still in the call stack. So we can just call B now and visit B, and we do. And this gives us access to node C finally. And this is the very last node we have to traverse. And we're going to put it in the stack and then pop C off of the stack. And now we've successfully visited all the nodes in this order of A, D, E, F, B, and C. Here's a representation of what our resulting array might be if you were to produce a resulting array of this traversal of depth first search. Now I want to show you what it would look like without the call stack. I just want an illustration of the vertical nature of depth first search and how it traverses nodes. So we started at A, that was our first visited node. Then we visited D, then we visited E, then we visited F. So notice this vertical pattern that we're making here. We're not approaching it horizontally, going A, then B, then D, then C, then E, then finally F. It's just straight down vertical. So A, D, E, F. And then now we have B still in our call stack. If we pop off B, gives us access to node C. And then we pop off C. We've now traversed the entire list, or entire graph rather. So that is depth first search in a nutshell. It's not too bad. And actually the code in JavaScript is, I would say it's not too bad either. So let's hop into that now. Okay, so here we have a depth first search function. I just called it DFS, and it's going to take a graph and a root node. So all the graph is just an adjacency list of the node names and their neighbors. Okay, so their neighbors are just put into an array. So each neighbor is just like that illustration that I showed you just before, and we're just putting the neighbors into an array, and the graph is just an object of nodes, right? So that's all this function is going to take. So right now I'm passing a graph, and then I'm going to use A as my root node. So the first thing you want to do, since depth first search uses a stack, we can just make a variable called stack, and then I'm going to pass in the root node, because that's going to be the very first node that we pop off or execute, right? So while I have something in the stack, so I'm going to say while stack length exists, we know we need to pop it off or we need to do something. So we're going to fire this while loop while there's something in the stack, okay? So Next, I'm going to make a variable called vertex, which is just going to represent the node itself. So recall that a stack uses the pop idea. So we're going to pop the top thing off the stack. So that's what the vertex variable is going to represent. In JavaScript, using the pop method will actually mutate the array and literally grab that top thing from the stack and pull it off and mutate the array. So just a heads up. So that's why I'm just using this const vertex. And then now we need to keep track of our visited nodes that we visited before. So the way I'm going to do that is I'll just make a variable called visited, and I'm going to use new set. A set is just a bunch of numbers or letters, but it doesn't allow for duplicates. So if you had like A, B, C, A, it would still just be A, B, C because the duplicate A would not be included in a set. So it's kind of a neat little feature you can use because you don't want to visit the same node twice. You only need to visit it once, right? So I'm going to say if we haven't visited a node before, then I want to add it to my visited node list. So I'm going to say if visited has vertex. Notice I'm using the not operator right here. This is the opposite of visited. So instead of saying, have I visited the node, I'm saying if I have not visited the node, I want to add it to visited. And then also recall from the illustration, I had like an array of the nodes I visited in order. I'm going to call that result and just set it to an empty array. And I'm going to add whatever we add into our visited. I'm going to also add that into the result array. So I'm going to say result push vertex. Okay. So now we've pushed the node we don't have or we haven't visited yet into the result array and also the visited set. So that's all good and dandy, but we need to also find the neighbors and deal with them. So what I'm going to do is just loop over the neighbors of each individual node. So I'm going to say let I equal 0, and then I is less than graph. This is where I'm using the graph part right here. Graph at vertex dot length, and then increment I. So recall that graph at vertex is just cycling through each of these nodes and grabbing the neighbors. So graph at vertex.length, if I was dealing with vertex B, this length would be 3 because I have 3 items in B. If I was dealing with node D, this length would be 2 because I have 2 neighbors of the node B. It has 2 neighbors attached to it. Okay? To kind of simplify that and make it a little bit easier, I'm going to say let neighbor equal graph at vertex, and then I have to use I, right? Because I is incrementing, and it's going to show me which one of these neighbors I'm pointing to. Okay, so I've got the neighbor, and we're going to do the same thing. We're just going to push that neighbor onto our stack. So I'm going to say stack push neighbor. Just like that. And that's all there is to it, really. Let's return the result array. And then let's run the code. And there you have it. There is all of our nodes traversed. You could even be a little tricky in this console. Let's do console.log vertex so we can see the nodes traversed. And it's the same order there, A, D, E, F, B, C, just like in the illustration. So it's really not that bad. Just recall that a depth-first search is using the stack, and you have to pop the vertex off of a stack. And that's the very thing on top that is a LIFO orientation. Okay, I hope you guys enjoyed this video. Please make sure to like and subscribe, and I will see you in the next one.